Assalamualaikum warahmatullahi wabarakatuh. And good morning.
Good morning to you.
Nice, good. All right, so let's start our class. So today will be this week we are having only one class because last Tuesday is a holiday. So and this is actually the last 2 weeks. So next week will be our last week, week 14. Okay, so we are very close to the end. Okay, so and this week we will start for the last part of our course, which is we will go for a filter design topic. Okay, so we have actually two types of filter. One is FIR, another one is IIR, right? So we will start with the FIR first. So, but before that, as usual, so let's do some recap so that we will know where we are. All right, so this one will be the whole thing that we're going to learn. So we have learned about what is the LTI system. So LTI system is a linear and time invariant system. Okay, so this is very important because with a linear and time invariant, so actually the system becomes a very practical. Okay, so instead of non-linear, so that one is a bit complex to implement. So linear system will be a very more straightforward system, and implementing it is will be a far more easier than a non-linear system. Same thing with the time invariant. So and we have start with we have covered about sampling because this is a digital, which is a discrete time signal and system. So we need a sampling to do that because originally everything is in a continuous signal. We do sampling, and then we have this relationship which is a t equals to n over fs, and then a system itself is actually you should have input, do something to it, and then you'll get output, a new signal. Okay, so this new signal is after some operation in our system. And to do the operation, so we need, in our case, the filter. So we have in our system now, because this is LTI system, so we have three things. So one is the input, and then the output, and then the filter. Okay, so this filter will define what will be the process that we will do. And specifically, uniquely for LTI system, the operation, we just have three operations. So one is just multiplication, and then summation, and then the other one is delay. All right, so we have only these three things. And with these three operations, so the relationship between the input, output, and the filter, so we call it a difference equation, right? So that's a difference equation. So we have a delay, multiplication, and summation only. So this is the things. And instead of a difference equation, so we can convert that operation into a convolution. Okay, so either you do a convolution, even the convolution is the same thing. This convolution is about delay, summation, and multiplication. So it's just that the form is different. So actually both are doing the same thing. It's just that the mathematical form is different. Okay, but everything is actually convolution. So then what we have done is first thing that we have learned after we do a sampling. So we already know what is a sampling, and we already understand what is a system. Okay, so then after that, so we have learned on how to analyze the filter. So we don't analyze the inputs, we don't analyze the output yet. Okay, first thing that we do is actually we analyze the filter. So, and analyzing this filter, the most important is on checking the stability and causality of the filter. And actually, we have covered three methods on how to check stability and causality. So one is on the difference equation itself. So where we are checking the input and output. So for example, stability, we are checking the Bibo effect. So whether it is a bounded input or bounded output. The second is we are checking on the impulse response. And the third one is actually we are checking on the ROC. So after we learn about Z transform. Okay, because this ROC is within the Z domain, the Z plane. So So those are the three methods on how to check stability and causality, because it is a very important to check stability and causality of a system, because if it is not stable, so then your output will not be stable. It means that the output will be haywire. Okay, and we need to make sure it is a causal, because if it is not causal, so it will depend on future value. And of course, practically, we do not know what is the future value. So we need to avoid that. Mathematically, stability is when it involves infinity value. Again, the same thing, our system will not be able to process infinity value. Okay, because even infinity is not a value. So that's why we cannot process. So, okay, all right. And then, so we have done, we have learned on how to, because we have learned on forward, so we have learned on inverse Z transform also. And then, so we have a very long weeks, after several weeks, so we learn about spectrum. So why do we need to learn this spectrum? Because we want to have more analysis. So we want to understand more on what is the input. So what should we look at the output? And how to understand the filter itself. Right? So we have learned, we already covered that for input signal. So why we do spectral analysis? Because we want to identify the frequency of the noise or the unwanted signal. Okay, and for the output, we just need to check the output. So is it check which frequency have been attenuated? Okay, because we are, let's say, when designing, we are expecting something at the output. So how to check? So we are checking the spectral analysis on the output. And also on phase, we are checking the phase distortion. So we have discussed this on the phase distortion, right? And we also do analysis, especially actually for the filter. Okay, and why we need to do analysis, the spectral analysis on the filter? Because we want to know actually, oh, what does this filter do? Which frequency will it remain? Which frequency that this filter will remove? So which frequency that this filter maybe just reduce or maybe increase? Okay, so how to do that? So we are checking on the magnitude. So we are checking on the magnitude. Right, and then of course today we're going to learn more on what is the pass band, the stop band, what is the transition bandwidth, what is the ripple, because when we want to design a filter, so we need to check this thing. Right, and another one is we're also checking on phase. So our filter, does it have a phase? Because we want to know at the output, is there any delay? So if it is a linear phase system, then we're not worried, because the delay for all frequency will be the same. But if it is not linear phase or zero phase, so the delay will not be the same for every frequency. So this is where we call it, it is what happened is a phase distortion. So it doesn't want that. So that's why we need to check at the outputs that phase distortion, if it's happened, does it really affecting our outputs? Okay, so that's why we need to check at the outputs, because sometimes it has a phase distortion, but it doesn't affect the output much. So, but some application, the phase distortion is actually affecting a lot. Okay, so that's why we need to check both. So one is on magnitude, which frequency will be remain attenuated, remove, reduce, or increase. And checking on phase, because we want to know what will be the delay at the output. All right, so, and we have also covered what we call a DFT. So DFT is the practical implementation of the frequency of the spectrum on doing the Fourier transform. Okay, because theoretically we can have a DTFT, discrete time Fourier transform, but the one is a conceptual and theoretical. So the practical implementation is on DFT, which is a discrete Fourier transform. So we have covered that, right? So this week and next week, so we will go to the last part, which is design. Okay, so we have these two designs. So this is IIR design, this part, and this is FIR design. So this week we will cover this one, FIR design. So how to design a filter. What does it mean by design a filter? So it is actually on how to get a filter coefficient. So FIR design, because of FIR, so the filter coefficient that we have is A fixed equals to 1. Okay, so it doesn't have to compute that, to find that. But the B, so we will have some values on coefficient B. So the objective of this design is actually the output. Our expected output is the coefficient B. And this coefficient B is actually equals to impulse response for FIR. Okay, so if you look here, before we go in detail, this diagram, so what we do is actually we are trying to find this Hn. Okay, so we will solve this equation. If you can solve this equation, then actually you are designing your filter. So we need to have some steps on how to solve this equation. So that's the only thing that we will do, solving this equation. You will get your Hn, because that's the output. That's the product of FIR filter design. Okay, filter coefficient B. And next week, so we will do IIR design, and this is a bit more complicated, because we don't only find one coefficient, so we need to find two coefficients. So one is a filter coefficient A, another one is a filter coefficient B. Okay, so there will be some steps also on how to get those filter coefficients, because those filter coefficient is actually representing the filter. So that's actually what does it mean by designing a filter, on how to find filter coefficient. Okay, all right. So this is where, if we those are the MATLAB function that you can use even in your assignment. I think most of the group already use either FIR1, or you can use this one, butter. Okay, so you use a FIR1 to get Hn for FIR filter. You can use a butter so to get the filter coefficient B and A, right? So that's you are designing the IIR filter. And if we do the grouping of this diagram, so you will see that. So those things are analysis. So those parts, this bottom part, so those are analysis. So the first thing that we learn is actually that one is the implementation. So implementation is we do either convolution or difference equation solution. Okay, so in order to do that, so you need input and the filter. So previously, we are already given the filter. Starting this week and next week, so we will design the filter. So we will find what is the coefficient A and B, right? And so this is the part where we have the design. Yeah, and actually, in your assignment for this week, which is the phase 2 part 2, so you can use this diagram as your guide, because in this diagram, so actually this is actually mapping. So actually you have everything. You have all the DSP keywords. Okay, you have a convolution, you have a Z transform, you have those Fourier transform. Everything is here, so you can actually use this as a guide on how can you have your own analysis mapping. Okay, so it's just that, of course, we don't have any plotting here, so you need your plotting because we have you have your input signal, which is the ECG signal. Okay, all right. So, any questions so far? So that's just some revision. All right, so now we already know that what does mean by a filter design. So actually for FIR filter design, so we want to find what is Hn. Okay, the impulse response. So then let's start. So digital filter design, filtering is a process of changing signals spectral content. Okay, so the change is usually to attenuate a range of frequencies in the signal while allowing the other frequency to pass through. So this is actually the normal objective of a filtering. So normally in filtering, we doesn't the objective that is not to increase the frequency content. Okay, so it's either to maintain it, or to attenuate, or to reduce, and if possible remove. Okay, so below are how Z transform and DTFT are used to design the filter. So we have two. So we have IIR and FIR. So this week we will do this, which is the technique is we call it windowing. So next week, we will cover IIR. So we cover only one technique, which is what we call a bilinear transformation. Okay, there are many other techniques on how to design IIR and FIR, but we will focus only one method for one filter. Okay, FIR, we will focus on windowing methods only. For IIR, we will focus on bilinear transformation only. And in designing this filter, how do we use a Z transform? Z transform is actually to convert an analog filter later next week. So we'll see what is actually analog filter, how to convert analog filter to digital filter. Okay, we will use a Z transform to do that. And of course, to obtain difference equation. So the output of a IIR is difference equation. Okay, because a difference equation is actually represented by you need a filter coefficient B and A. If you have a filter coefficient B and A, so you can have your difference equation. Right? So for FIR, actually we just try to get what is the HN. Right? So that's the difference. Because IIR, practically, we cannot do convolution. So that's why we try to find what is the difference equation so that we can do a solution to the difference equation. FIR, why we do a HN, which is the impulse response, because we can use that impulse response to do convolution. Okay, so after you have your HN, impulse response, then do convolution with your input signal. And because FIR, we can do convolution. Practically, we can do convolution. All right, so it's just conceptually and theoretically, actually both are doing the convolution, but practically IIR, we cannot do that. So, and how do we use the DTFT? DTFT, we will use that to analyze the spectral response. Okay, so this is to design and this is to analyze. So we're going to use this DTFT or DFT. Okay, because the DTFT is the theoretical concept, and DFT is actually the practical implementation of the Fourier transform. So what's important is we need to analyze the spectral content. Okay, so we use these two. Okay, before we go to more detail on what is actually a filter, so let's see what is actually ideal filter. So ideal filter, we will have only one parameter, so which we call a cutoff frequency. So for example, this is actually what we call a low pass filter. Right, so if you still hopefully everybody realize this is a half plot. Okay, so we have three types of plots. So we have a whole plot, so which if we use the omega, the range will be from 0 up to 2 pi. So we have a shifted plot, so where the range will be from minus pi to pi. And then lastly, we have actually half plot. And actually half plot is enough for analysis. Because the half plots will be from 0 up to pi and at pi. So this is actually our maximum frequency. Okay, so then it's enough because the other parts from pi to 2 pi, that one is the conjugate pair of the spectrum. So doing analysis, we doesn't have to look to observe that part because it's just a conjugate pair of the section of a 0 up to pi. So this is the only section which is important. Okay, so what is a low pass filter ideally? Ideally, so we have the magnitude. The magnitude should be 1 for those frequency that we want to pass through. Okay, so that's why we call it a low pass. The lower frequency will be passed through. So that's why the name is a low pass filter. And the higher frequency part will be multiplied because what is output? Output is our input spectrum. You just multiply with the magnitude of your filter. Okay, so if you want to remove some frequency here inside your input, because the operation is multiplication, so you multiply with 0. So those which where you multiply with 0, then you will remove that frequency. Okay, and the one that you want to preserve, you multiply by 1. So it will be preserved. So whatever the magnitude of the frequency on input signal that you want to preserve, multiply by 1. So it will remain. It will be preserved, because anything multiplied by 1 will be exactly the original value. Anything multiplied by 0 will equals to 0. So that's ideal filter. So it is quite easy, because that's why in LTI system, so we can have this thing. Okay, so this is actually for the LTI system. So even the filtering is quite easy to understand, because the operation is just multiplication. All right, so what we have here is actually one parameter, what we call a cutoff frequency. So this is what we call a cutoff frequency. Okay, and of course, this is not the first time that you heard the term cutoff frequency. So you have heard about this cutoff frequency many times before, right? So what is a cutoff frequency? Cutoff frequency is just where this magnitude change value. So for low pass filter, so it is when it's changed from 1 to 0. So that's what we call a cutoff frequency. Okay, means that frequency below the cutoff frequency will be preserved. Frequencies which is above the cutoff frequency will be removed. Right? Okay. So this is how is it. If you want to put it in equation, so we can put it such this. Okay, so it will be 1 for omega less than or equals to omega c. And it will be 0 for omega c, for omega, which is greater than omega c. And of course, less than pi, because pi is the maximum frequency. Okay, so, and other example is, this is a high pass filter. So high pass filter is the opposite of a low pass filter. So we will have a 0 for the lower frequency and 1 for the higher frequency, right? So omega c is where the transition of the frequency from magnitude 0 to magnitude 1. And this is the equation. And if you want to to develop this high pass filter, you can do it from low pass filter. So it is just 1 minus your low pass filter. So it means that you can have a low pass filter first and then create a high pass filter just by doing this equation. So just put 1 and then minus the magnitude of the low pass filter. Okay, so then you will get a high pass filter. And actually any filter can be designed, can be developed or created from a low pass filter. So this is an example of band pass filter, and this is band stop filter. So any filter is actually can be created from a low pass filter. So band pass filter, you can have this. So you will have a 2 low pass filter. So this is one low pass filter at cutoff frequency number 2. So we have, because we have a 2 cutoff frequency for band pass filter, because this is the shape. So this is the first transition, and this is the second transition. Right? So that's why we have a 2 cutoff frequency. So then if you want to create this band pass filter from low pass filter, so you can have this equation. So a low pass filter with the cutoff frequency of the second cutoff frequency minus low pass filter using the first cutoff frequency. Okay, and then this is a band stop filter. So what you have is just whatever you have here. So 1 minus this thing. Okay, then you have a band stop filter. And any filter, any other filter, because this is the 4 basic filter, any other filter is basically you can create using a low pass filter. So this is why when we actually learn on how to design a filter, so we will learn the low pass filter, because the rest is actually you can just create it from a low pass filter, right? So we just learn on the low pass filter, and then if you need other filter, you just create it from the low pass filter. Okay, that's actually an ideal filter. Ideal filter is actually we just care about one parameter, which is the cutoff frequency. But we not always can have that kind of ideal filter. So because practically we will have what we call a non-ideal filter. So that's why we need to learn on, we need to control this parameter, because the non-ideal filter, we have a lot of parameter that we need to control. Okay, when we design a filter, we need to take care of all these parameters. So other than cutoff frequency, so we have omega p, omega s, delta p, delta s, and this capital N and delta omega. Okay, so there are a lot of other parameters. So, but basically, it is actually what we have is on, we can group this actually into one is of course the cutoff frequency. Number two, actually we need to take care of what we call a ripple. And number three, the transition bandwidth. Because actually we need to control these three. So cutoff frequency, ripple, and transition. But from these three, so we have all these parameters. For example, this omega p, which is the passband H frequency. So this is actually coming from the transition bandwidth. Okay, a parameter which is related to transition bandwidth. The same thing with omega s and delta p. So you have seen this. This is a ripple. So this is actually related to ripple. This is also related to ripple. And a filter order, so it control both ripple and transition bandwidth, okay, indirectly. And this one is a transition bandwidth. Of course, this is directly what it means by a transition bandwidth. Okay, so let's see. Graphically, so these are all the parameters. So if it is a non-ideal filter, so this is actually basically what you will have. So instead of a very straight line, okay, so now you have a ripple. So this is what we call ripple. And then this is another ripple. So this is actually the pass band ripple. And this is a stop band ripple. Okay. And we have transition bandwidth. So ideal filter, there is no transition bandwidth because if you look here, the transition is only at omega c. So from 1, just suddenly becomes 0. Okay, there's no transition bandwidth. But a non-ideal filter, so you will have a transition from this high value into your low value. Okay, so ideally, so we need to have 1 here. So actually, the ideal filter so that's supposed to be the ideal filter. But this straight line, now we are having a ripple. This straight line, so now we have a ripple. And this straight vertical line, so now we have a transition bandwidth. Okay, so and on this stop band, on the stop band frequency, this one, so that what is the peak? So this is what we call, if you look here, delta 2, delta. So I'm using a different thing. So this is actually a delta 2. This is delta 1. Okay. So that one is what we call a stop band ripple. So this one is a pass band ripple. So what is the pass band ripple? So this is the pass band. So those are actually the ripple, that delta 1. Okay, so how do we measure it? This is supposed to be 1 because ideally this is 1. The magnitude is 1. So here, from here to here, so that one is what we call a delta 1. So which is a 1 plus delta 1. So the lower part, so this is 1 minus delta 1. Okay, because it's supposed to be 1, but we didn't get that on an ideal condition. So it's not a straight line of magnitude 1. So we have a ripple. Okay, so we need to control that. And then this is the transition bandwidth. So we have, this is what we call a pass band H frequency. So this is omega p, and this is the stop band H frequency. So we are measuring somewhere from here, so until it goes down to this is the ripple, so somewhere here. Okay, so there will be some definition later. So what will be from what is the omega p until omega s? And in the middle of omega p and omega s, because ideally so we should have this one, omega c. So omega c is actually located between omega p and omega s. So what is the omega c? The cutoff frequency. Okay, and if we look at the magnitude, so we can call this the magnitude at, so this is the magnitude at cutoff frequency. So which is the magnitude of h omega c, right? And we will see that this magnitude will be fixed at certain value. Okay, later we will see that. So this one will be fixed at certain value. So for FIR, so there is a one value. For IIR, so there is another value. Okay, and it is fixed. It is fixed. So the rest is actually depending on the on the design. Okay, all right. So okay, those are actually the mathematical derivation of the things, and this is the techniques. So we're going to cover windowing technique also. So actually we have a frequency sampling technique. We also have an optimum technique, but we're not going to cover those two. Okay, and of course it's not limited to these three. So we have other methods. So, but for this course, because we want to have some idea on how to design an FIR filter, that's it. So we're going to just cover a windowing technique. So when we look at this, so actually designing a windowing technique, why we call it a windowing? Because designing FIR filter, okay, the second facts here, is actually based on basically it is doing by truncating ideal filter. Okay, so actually this is the idea, truncating ideal filter. So what is that? We will look at that one. Okay, so but this is actually the idea, truncating ideal filter. So which is the ideal filter is actually IIR filter. So after we truncate this IIR filter, so it becomes FIR, right? So let's see. So that's actually the idea. And this is just one example of the spectrum of a filter that we design. So, and in this case, so we have our cutoff frequency at 0.5 pi, okay? And then this capital N is actually filter order. So we have a filter order equals to 20. And the window is equals to a rectangular type. So we'll see that, what is actually window. And then, so this is 0.4, the passband H frequency. So this is the 0.6 pi is the stop band H frequency, right? So, and then we know that the transition bandwidth is 0.6 pi minus 0.4 pi. So that will be the transition bandwidth. Okay, so and then so we can measure also the ripple. So this is actually the ripple. So this is the maximum peak. So that one will be the ripple. Okay, and this is the stop band ripple. So now we will see that. So how do we control those things, right? And this is the procedure on how to design it. Okay, so actually in this slide, so we have if you look at this filter design procedure, step 1, and then there's a step 2, and then there's a step 3, a bit long, step 4. And we also have, after those things, because those are a bit a detail on what are the steps. And this is actually a simplified steps. Okay, so and we will focus on this one because we doesn't want to go for a lot of detail here, because if you go to a lot of details, there are a lot of theory behind it. So if you are interested on knowing what is actually the detailed explanation on it, so you can go for these 4 steps. But a simplified steps, so we have only 3 steps. So what is the step number 1? So on designing this FIR filter, so it's actually determine cutoff frequency. Okay, so that's the first thing. I think some of you already done this because in assignment phase 2 part 2, even part 1 actually, so you need to come up with a MATLAB code on how to remove the noise of the ECG signal. Okay, so I think you have come to this step, so which is you are choosing the cutoff frequency. So how to get this omega C? So either manually specified. So this is where you either you do a try and error and then get what is the best cutoff frequency, or it can be computed from a transition bandwidth value because some design. So actually we specify what is the transition bandwidth. And then you can get your omega C, the cutoff frequency from a transition bandwidth. Step number 2, after you get the omega C, so you will determine the filter order and window function. Okay, omega C, first step. Second step is the filter order, which is the capital N, and then the window function. So after you have those three, so the next step is to solve this equation. So this equation is actually directly impulse transform. So because in this equation, so why do you need to have a step 1 and step 2? Because in this equation, so you have omega C here. So you need to find it here. And then it has also capital N, which is a filter order. So that's why you need to find a filter order here. And the filter order is actually related to window function. So this is actually the window function. Okay. So after you have those three, then solve this thing. Then you're done. So you get your FIR filter. Because this FIR filter is actually represented by impulse response, which is HN. All right, and okay, let's go for a little bit more detail on the steps. So this is actually how we design the FIR filter. Normally we start at a spectrum because we need to identify what is the cutoff frequency, what is the transition bandwidth, because in certain design you should have this. For example, let's say if you have those ECG signal, so first you need to identify where is the which frequency actually the noise is on. Okay, so I identify that one first. So let's say the noise is somewhere here. So that's why you need to pick cutoff frequency before the noise frequency. Okay, because and then of course you need to identify your required frequency. Okay, which frequency needs to be maintained. So for ECG signal, of course, you need to maintain the ECG signal, and you need to remove the frequency of the noise. So identify where is the noise frequency and then where is the ECG signal frequency, and then you should put your omega C in between that. Okay, so that's how you pick omega C. So this is how you need to have your you need to analyze the spectrum for the input signal. So from input signal, doing those analysis, you will know. So you will know. So then you have the omega C. So that's why the first step is determine the cutoff frequency. So how to determine the cutoff frequency? You need to analyze the input signal. Identify what is the frequency, that is the noise frequency or unwanted frequency, and identify which one is your desired frequency to be preserved. Okay, then put omega C in between those frequencies. So this is where you can do either empirically it's a try and error doing that, because sometimes the frequency of the noise and the frequency of your desired signal might be overlap. Okay, so it's not always separated. So it can be overlap. So this is where when it is overlap, so maybe you need to do some try and error. So which omega C will be the best, right? Or you can get it from a transition bandwidth, because sometimes you are given a spec. So you're not looking at the inputs. You're not looking at the input spectrum, but you are given a spec. Okay, and in that spec, it says that you need to have a transition bandwidth of a certain value. So this is where actually this delta omega This is a transition bandwidth. Transition bandwidth is actually equals to omega S minus omega P because it is actually in between those things. And we know that omega C is actually just omega P plus omega S divided by 2. So it is in the middle between omega P and omega S. So either you do try and error for omega C, or if you are given a spec, so which is you will know what is the transition bandwidth, you will know what is the omega S and omega P. So you should compute omega C based on those values, right? So those two things. So then after that, so we need to determine a filter order and window function, because a filter order and window function is related. So this is actually the window function. So this is the window function in time domain. So if you look at this diagram, this plot, so if you realize that, so this is the x-axis is n. So this window function is in time domain. This, of course, a spectrum is in frequency domain, right? So do not get confused. Our window function is actually, we are giving the window function in time domain, not in spectrum. So then we need to choose that. So we need to choose that because a different window function, let's say there are several types of window function. We have a rectangular, we have a Hamming, Blackman. So these are actually the shape of our window function. The easiest is rectangular. Rectangular is from 0 up to your some certain value here, m. So everything is just 1. Okay, so that's the function. Very easy. Everything is just 1. Okay, so the one that we have seen in this example, so this is actually maybe we can say that this is Hamming. So because the rest is we have this curve, a bell shape of window function. Okay, it's just a little bit different. So this is at this line. This is wider. This is less wide. This is what we call a Blackman. So this is a Hamming. Okay, even though it is a little bit different, but it gives a different effect, right? So these are the window in time domain. So we need to choose that because why do we need to choose that? Because let's say rectangular, Hamming and Blackman. So it will give you a different ripple and a different transition bandwidth. Okay, so this is the transition bandwidth and this is your ripple. So if you want to have a certain value of a transition bandwidth, so what is the transition bandwidth for rectangular? Rectangular is a 1.8 pi divided by n. So that's why you need to choose n and window function at once. Because if you choose, let's say, n equals to 10, so what will be the transition bandwidth if you choose the rectangular? So it will be 1.8 pi divided by 10. Okay, so it will be a 0.18 pi. Okay, that's the transition bandwidth. So Hamming, so it will be a 6.2 pi. So you will have a wider transition bandwidth. And this is even wider. And this is even wider. Okay, so the best transition bandwidth is the smallest transition bandwidth will be the best. Okay, so if you look at here, so actually rectangular will have the best transition bandwidth because it has the smallest transition bandwidth. So because everything depends on the n, but we have a fixed value here. Okay, so depending on your spec, depending on your situation. So if let's say you have the separation between the noise and your desired frequency is quite far, then maybe you can have a wider transition bandwidth. But if the separation of the frequency of the noise and your desired frequency is very short, so maybe you need to consider a small transition bandwidth. Okay, in this case, maybe a rectangular window is maybe the best because it has the lowest transition bandwidth. But we need to balance that because if we look at rectangular, the ripple is the highest So the worst ripple is actually for rectangular. Even though it has the best transition bandwidth, actually it has the worst ripple. So minus 20.9 dB. So that's actually quite big. Okay, compared to, let's say this is Henning. So this is a minus 20, minus 43. Because of course, a minus 20 is bigger than. So we know that minus 20 is bigger than minus 43. Okay, so because we are looking this at a dB spectrum. Okay, if you remember, so we can plot our spectrum based on real and imaginary. Doesn't give us much information, but then we actually plotting it based on magnitude and phase. And we have other types of plots, which is we can have also a power spectrum, which is a magnitude square. Okay, and we have another one, which is a magnitude dB. So this is actually magnitude dB. Okay, it is actually a better way of visualizing our filter if you want to analyze the ripple. Okay, transition bandwidth is fine. Actually, we can do it on a normal magnitude, but checking ripple, so actually it is best to visualize it in dB, in magnitude dB. Okay, so that's why everything is in dB here. So minus 20 dB is a bigger compared to minus 43. And black man, this is actually the lowest ripple. So because this is opposite, so this is why you need to balance. You need to determine what is the N, and then you need to balance. So how much transition bandwidth that you can have, how much ripple that you can have. Okay, so then you need to balance between these two. So this is why it's not always a rectangular is the best, because rectangular is just based on transition bandwidth, but it's worse on this ripple. Okay, so depending on your filter, so you need to choose. You need to choose this filter order and the window type. Okay, so you have that. So after you have those three, omega C, the capital N, and the window function, so then, so we will solve the impulse response equation. Okay, because we just need those three parameters, omega C, the capital N, and window function. So then solve this equation. Okay, so we have seen this equation. So actually, what is this? So this is omega C over pi of and then multiply to sinc. So this is a sinc function. So sinc of omega C divided by pi and then multiply to n minus capital N over 2 and then multiply with your window function. So this is the window function. So this is actually your window function. So this is that green plot. So this is your window. Your window is center is always 1. Okay, and then the value will be decreased. Okay, the value will be decreased, but the center is always the amplitude is 1. And this green plot, so this is actually a sinc signal. Right, this is actually a sinc signal. So that sinc signal is actually a start from minus infinity up to infinity. Okay, so that's actually the original sinc, because this sinc value, this sinc signal is actually coming from an ideal filter. So that ideal filter, without any ripple, without any transition bandwidth, if we do an inverse Fourier transform of this ideal filter, you will get a sinc function. You'll get a sinc function. But what is the problem with this sinc function? It is not FIR. It is IIR, because it starts from negative infinity up to infinity. Okay, so that's the problem. So then how to solve that? So we need to limit. So we need to limit this IIR impulse response. So doing that is because this is where the windowing methods comes in. So you have your omega n here, so which start from 0 up to n. Then we just multiply these two. Okay, so multiply these two. So then whatever the value here, the window function value here is 0. So whatever the value you have here, multiply with 0, so it will be gone. It will be 0. Whatever the value that you have here, multiply with 0, because the value is starting only from 0 up to n. The rest will be 0 for the window function. So multiply with 0, you'll get 0. Okay, then the center you multiply by 1, so it will stick to omega c over pi, and then a little bit decreasing value, this one. Okay, just to make sure that the transition, because we doesn't want to just remove this, and then you will have not a smooth transition. So that's why this is actually just to make sure that the one that you remove and then the one that you preserve, the transition becomes smooth. So that's why this value is actually a decreasing value. So we need to do that. Okay, because by doing that, so you will reduce ripple. Okay, you will reduce the ripple. Okay, so this is what you will have after finishing everything. Okay, so now this is FIR because you already multiply with your window. Okay, it starts from 0 and then it will end at capital N. Okay, finish. So that's your, and this sinc function, which is a limited sinc function, is actually, if you do Fourier transform this one, you will get this one. So this is actually the one that we desired. So the filter that we desired, so we all the parameter we set it on the frequency domain, and then after that, so you will have this thing, solve it, so you will have the your Hn in time domain. Okay, so that's the 3 steps. That's the 3 steps on how to design an FIR filter. So any questions? So I think we doesn't have enough time to do one example. So we will look, we will go for examples on next Tuesday. Okay. All right. So any questions? So we'll go to this example next week, right? Tuesday. So if there is no other no questions, so we'll that will be the end of today's class. Okay, thank you. Assalamualaikum and good morning to everybody. So see you guys next on Tuesday.
Thank you so much.